Stephen Hawking here, and I want to share with you something that completely transformed my understanding of the universe during my years as a physicist at Cambridge. You think you understand time, you look at your watch, see the seconds ticking by, and believe you know exactly what time is. But what if I told you that Albert Einstein's revolutionary insights about time would change how you see reality forever? Most people never really ask these fundamental questions because they assume time is simple, just a clock on the wall and a calendar on the desk. But when Einstein examined time closely in 1905 as a young clerk in a Swiss patent office, he discovered through pure thought experiments that time is not what you think it is, not a background against which events happen, not universal, and not even fixed in any real sense. By the end of this, you will never look at a ticking clock the same way again, because you'll understand what Einstein showed us, that time and space are woven together into a single fabric called space-time. Right now, as you watch this, you are traveling through time, not in some science fiction sense, but genuinely, measurably, moving into the future at exactly 1 second per second. That rate is not fixed, and it can change based on Einstein's special relativity. If you were to stand up right now and start moving around the room, time would pass differently for you than for someone sitting perfectly still. The difference would be far too tiny to notice, but it would be real, measurable, demonstrable. And it gets even more peculiar because of general relativity. If you were standing on top of a tall building, time would be passing very slightly faster for you than for someone on the street below. This gravitational time dilation is not theoretical. It's why GPS satellites require constant atomic clock adjustments, because without accounting for Einstein being right about time, your navigation would drift by about 10 kilometers per day. When I was a student, this struck me as quite possibly the most extraordinary discovery in the history of physics. Not because it was counterintuitive, though it certainly is, but because it revealed something about the nature of reality itself. Time is not a river flowing at a constant rate, but more like a landscape in Minkowski spacetime, where different paths through it take different amounts of time. Einstein's insight through thought experiments seems almost childlike in its simplicity. He asked what would happen if the speed of light is the same for all observers, regardless of how they are moving. If you are standing still and measure the speed of light, you get about 186,000 miles per second. Common sense says if you are running very fast in the same direction, you should measure the light moving more slowly relative to you. Einstein said no, you would still measure exactly 186,000 miles per second. The consequences of this simple assumption were devastating to common sense, because if light travels at the same speed for everyone, then space and time themselves must be flexible, stretching and compressing to keep the speed of light constant. The theory of relativity forces us to change fundamentally our ideas of space and time. We must accept that time is not completely separate from and independent of space, but is combined with it to form space-time. When you move through space, you are also moving through time, and here's where it gets interesting. There's a trade-off. The faster you move through space, the slower you move through time. This is not philosophy but physics, tested with atomic clocks on aeroplanes. The clocks that moved came back running slightly behind the ones that stayed on the ground, by exactly the amount Einstein predicted. Consider the famous twin paradox. Two twins where one stays on Earth and the other travels to a distant star at nearly the speed of light, then returns. When the traveling twin comes back, they will find their sibling has aged significantly more than they have. If the journey took 10 years for the traveling twin, decades might have passed on Earth. This is only a paradox if you have the idea of absolute time. In relativity, there is no unique absolute time, and instead, each individual has their own personal measure. Einstein's general relativity made an even more revolutionary suggestion. Gravity is not a force like other forces, but is a consequence of the fact that space-time is curved or warped by the distribution of mass and energy. When you drop a ball, it doesn't fall because some invisible force pulls it down, but because the mass of the Earth has curved space-time around it, and the ball is simply following the straightest possible path through that curved landscape. Gravity doesn't just curve space, but also curves time. And the stronger the gravitational field, the slower time passes. This is where my work with black holes became crucial to understanding time's deepest mysteries. Let me make this concrete with black holes. What remains when a massive star collapses under its own gravity into what John Wheeler first termed a black hole. The gravitational field becomes so intense that within the Schwarzschild radius, at what we call the event horizon, not even light can escape. Imagine you have a friend investigating a black hole. From their perspective, nothing particularly unusual happens as they cross the event horizon. But from your perspective, watching from a safe distance, you would never see them cross it, ever. As they approach, you would see them moving slower and slower, their image becoming redder and dimmer, appearing frozen at the edge, suspended in time forever. In 1974, I made a discovery that changed how we think about black holes. Working with insights from Jacob Bekenstein's earlier work on black hole entropy, I showed that black holes are not truly black. They emit what's now called Hawking radiation. This happens because of quantum effects near the event horizon, where empty space roils with particle pairs constantly popping into existence and annihilating each other. Near a black hole, one particle falls in while the other escapes. That's Hawking radiation. Black holes slowly evaporate this way, and this discovery was recently confirmed by LIGO's gravitational wave detections, which detected the space-time ripples from black hole mergers, validating Einstein's predictions and our understanding of these extreme objects. But this raises a disturbing question about time's nature. If time is just another dimension of space-time, does the future already exist? Roger Penrose and I have spent considerable effort on this question. In physics equations, there's no distinction between past, present, and future. The laws work equally well forwards and backwards, yet we have a strong sense that time flows in one direction. I believe the answer lies in what I call the three arrows of time. The first arrow is thermodynamic, the direction in which disorder increases, following the second law of thermodynamics. Consider a cup of tea, pour in milk, and it swirls and spreads evenly. You never see the reverse, never see milk spontaneously separate and jump back into the jug. The second arrow is psychological, the direction in which we remember the past and anticipate the future. We remember yesterday, but not tomorrow, because our memories are records of increasing entropy. The third arrow is cosmological, the direction in which the universe expands. Since the Big Bang, some 15 billion years ago, confirmed by the cosmic microwave background radiation, the universe has been getting larger. At the Big Bang, the universe was in an extraordinarily ordered state, extremely hot, dense, but remarkably uniform. As time passed, it became more disordered, with stars forming and burning out, galaxies scattering, and entropy increasing. This brings me to what I consider one of cosmology's most important questions. What happened at the beginning? What started time itself? In 1983, my colleague James Hartle and I proposed the no-boundary proposal for the universe's origin. Imagine Earth's surface. If you travel south, you reach the South Pole, where you cannot go further south. But there's nothing special about the South Pole. It's not a boundary, but simply a point like any other. Time might work the same way. As you go back towards the Big Bang, time doesn't end at a sharp boundary, but rounds off, like Earth's surface near the pole. The universe would be completely self-contained, not determined by anything outside the physical universe we observe. The laws of physics hold everywhere, including at the beginning, with no need for anything outside, no clockwork to be wound up. What this means for you is that every moment of your existence is far more mysterious than you ever realized. When you wake up tomorrow, you'll be a slightly different person, not just metaphorically, because the atoms in your body will have moved. Light from distant stars will have shifted due to space's expansion, and time will have passed slightly faster for your head than your feet, because your head is further from Earth's center. Every time you move, you're literally changing the rate at which you travel through time. Every time you climb a hill or descend into a valley, you're adjusting your journey through the fourth dimension. You're not just living in time, but navigating it. The universe is stranger and more wonderful than we imagine, because the fact that time can stretch and contract, that it began with the universe and is woven into its fabric, points to something profound about reality's nature. Ever since civilization's dawn, people have craved understanding of the underlying order in the world. Einstein once asked how much choice God had in constructing the universe. Even if there's only one possible unified theory, it's just rules and equations. What breathes fire into the equations and makes a universe for them to describe? Why does the universe bother existing? If we discover a complete theory, it should be understandable in broad principle by everyone, not just scientists. Then we shall all, philosophers, scientists, and ordinary people, take part in discussing why we and the universe exist. If we find that answer, it would be the ultimate triumph of human reason. Then we would know the mind of God. The next time you glance at a clock, remember what you're really seeing. Not just a device counting seconds, but a window into existence's deepest mysteries. Time is not a background against which events happen, but part of the event itself. It can bend, stretch, and under extreme conditions, stop entirely. That's what time really is. Not a river carrying you along, Not a relentless march from past to future, but a dimension of reality itself, as malleable as space, as fundamental as existence, and far stranger than any clock's ticking could suggest. And if that seems too strange to be true, well, the universe has never much cared about what seems reasonable. Understanding it, even partially, is one of the greatest privileges of being human.